Good afternoon. So in today's lesson, we will have a classification of certain types of partial differential equations, of which our two default examples, the heat equation and the wave equation, are essentially particular cases of. So basically, we will deal in this class with a method of solving what's called linear second order partial differential equations. As you might already realize, going through these types of topics, the class of partial differential equations is huge. So classification is essentially, a difficult task because it's too large to hope to categorize all of the partial differential equations. Even the linear ones are often really complex, so that you have essentially subcategories. So as I said before, we deal in this class primarily with linear equations of second order. And the goal of today's lesson is to basically write these type of equations in a more general setting, to describe several types of these equations and why we classify them in these subtypes, and to finalize with one of the most important, or if not the most important, concept that leads to our method of solutions, namely the superposition principle, which you will see playing a role shortly after this lecture. And some of the stuff in today's lesson is kind of analogous to ordinary differential equations, and in fact, let me actually write down as a remark, for those of you who remember maybe from differential equations, we had typically a dependent variable y depending on t, and a linear ODE in y of t had the general form of a linear combination in the derivatives of y. So for example, let's say if the ODE was of nth order, so going up to the nth derivative of y, then the format would be a function of t times the derivative with respect to n, times the n derivative plus another function of t times the n minus 1th derivative, going all the way up to a1 of t times y prime plus a naught of t times y equals maybe a function that depends on t only if the equation was not homogeneous. So you had a linear combination in y prime, y double prime, y to the nth, the n derivative. So that's what makes it linear. The fact that the dependent variable and its derivatives will be in a linear combination with coefficients that may depend on t. They could be constant, but in general they can depend on the independent variable t. And this whole left-hand side, if you write the equation this way, this is also called a linear operator. So the goal in today's lesson is to simply classify certain types of PDEs in the same manner to illustrate what we mean by a linear PDE. And like I said, some subtypes, some classifications by subtypes of these linear PDEs, and then put the wave equation, the heat equation in some sort of a context, basically. What we call the superposition principle is something that you actually used in ordinary differential equations, except here will be a little twist compared to what we have in the ODE case. So let's say in general that we have a dependent variable in a PDE that depends on two variables, x and y. Typically one of these is the time t in our heat and wave equation. Then a second order linear PDE in u of xy has the general form given by some constant u partial x twice plus b u partial xy, so mixed derivative here, plus c u y twice, then possible terms that depend on a single partial derivative, so u partial x plus some other constant e, u partial y, plus maybe some constant f that's multiplied by u itself, equals some constant g. And again, u stands for u of xy, and this basically can be any constants, these combinations here, including 0. So notice that the same concept occurs as in the linear ODE, that what constitutes basically a linear equation in our dependent variable u is the fact that u and its derivatives, which can be many of them now, first order, second order, right? This goes up to the second order because you have, you know, differentiated twice at most, uxx, uxy, uyy, right? So second order linear ODE, but it's the same concept. What makes it linear is that u and its derivatives, partial derivatives in this case, appear in some sort of a linear combination, in this case with constant coefficients. Okay, now I want you to notice that, well, we'll get to that actually later. I wanted to basically match this with the wave and the heat equation. But before we do this, there is a subclassification of linear PDEs of this form, depending on some relationship of the coefficients a, b, and c. And this classification is because if the equation falls in that category, then some clever substitutions will allow you in some cases to actually simplify the equation or even to solve for its general solution. And the name of these subclassification are essentially analogous to geometric objects by essentially making some sort of comparison between these three terms in the PDE with the curve ax squared plus bxy plus cy squared. So you don't have to bother too much about this because I don't want to get people confused. This has nothing to do with the solution of the PDE. But by making this analogy of these three terms with the curve in the xy plane given by these coefficients, and that curve could be a parabola, a hyperbola, or an ellipse, then depending on the relationship of these coefficients, you have what we call hyperbolic, elliptic, or parabolic equation. So this PDE is called hyperbolic if b squared minus 4ac is greater than 0. It's called elliptic if b squared minus 4ac is strictly less than 0. And parabolic if b squared minus 4ac equal to 0. And there is a long homework question, homework problem that I'd like you to take your time to go through it. What makes it long is that you will have to do a lot of differentiation via the chain rules. But you know, that's homework question essentially teaches you how you actually handle, how you can simplify these equations and even solve them in some cases by making some clever substitutions. And that clever substitution is predicated by whether the equation is hyperbolic, elliptic, or parabolic. So let's look at some of our examples that we went over already. So if you look at the heat equation in one dimension, the one that we typically write it like this, ut equals uxx k times uxx, and remember in this case u is a function of x and t. If I write it exactly like in the general form on the left, I'm going to keep the second order derivative on the left and then move the ut to the other side equal to 0. So notice that if I match it with the general format, pretty much all the coefficients are 0 except a. So a stands for k. There is no uxt, so there's no mixed derivative, so b is 0. There is no utt, so then c is 0. And then d will be 0. E will be actually minus 1. See, instead of y you have t basically. F will be 0, and then g will be 0. So if I look just at the values of a, b, and c, and compute b squared minus 4ac, that's going to be 0 minus 4 times k times 0. So it follows that the heat equation is parabolic. It's a parabolic equation because it follows on this category, b squared minus 4ac equals 0. What about the wave equation? The wave equation looked like this: ytt equals a squared yx twice. Again, if we write it in the standard format, then big A is a squared, big B is 0, and then C is minus 1. And so then for b squared minus 4ac equals 0 minus 4 times a squared times c, which is minus 1 for a squared greater than 0. And therefore the, the wave equation is hyperbolic. All right, what about an elliptic example? Well, for example, the steady state temperature equation for, let's say, the heat equation in 2 dimensions. So you have the Laplacian times k on the right hand side. So the steady state temperature equation will be uxx plus uyy equals 0. In this case, A will be 1, B will be 0, C will be 1. And then b squared minus 4ac is going to be 0 minus 4 times 1 less than 0. So therefore the steady state temperature in the 2 dimension is an elliptic equation. So remember, take your time to go over that problem because you will see the value of this classification if you go slow on that problem to see how it goes. Of which essentially wave equation, what we did with the wave equation to obtain the general formula, that's basically a particular case of that technique. So on the next page, I'm going to talk about, well, we mentioned this already, but let's write it down more formally, what we mean by a homogeneous linear equation. We also, like in ODE case, we have the distinction between linear homogeneous, linear non-homogeneous equation. So stay tuned for the second page. So before you continue, just a small rectification. These A, B, C, D actually can be function of x and y, just like in the single ODE case, like in the ordinary differential equation. So they can be constant, and they are constant in many cases, like in the case of heat equation or the wave equation. But they can be functions of the dependent variable, x and y in this notation, or xt in the wave or heat equation. So the coefficients of u can be functions in this linear combination. So now another important definition: a linear PDE in this form that we wrote above is homogeneous if g of xy and its possible boundary conditions are 0. So it's very important to remember that when we talk about homogeneity, whether the linear problem is homogeneous or not, then the 0 requirement, you know, what makes it a homogeneous problem, refers to both g of xy, I mean the right hand side of the PDE, the one that can depend on x and y alone, and any possible boundary conditions you may have. So, for example, let's formulate some boundary value problems. So let's say we have ut equals kux twice, so a heat equation with u of 0t equals u of 10t equals 0. And then let's say the initial condition is u of x0 equals, I don't know, let's say some function of x, which we won't specify right now. So this will be basically an object of length 10. this is homogeneous because, so it's a homogeneous PDE, their g of xy is 0. So if you move all the u's on one side, you don't have to do that, by the way, because we don't need to do that when we solve it. But when we move everything to one side, obviously g of xt, right, which stands for that right-hand side term, is 0. So that's homogeneous. And also the boundary conditions are 0 as well. So as a full boundary value problem, this is homogeneous. This will be basically a problem in which we have the endpoints of the bar, of the heated bar, kept at temperature 0. Here's another example. Let's say you have a heat equation in which you have ut equals kux twice. And let's say the left endpoint is kept at 0 temperature, but the right endpoint is kept at 5 degrees. Because of this condition, the entire boundary value problem is not homogeneous. We will need a separate method to deal, because we will solve the homogeneous one first, just like in the ODE case. But we will need a different method to deal with that non-homogeneous condition. So the failing to be homogeneous again can appear because of the PDE itself or the boundary conditions. So for example, let's say you have a heat equation in which you have some external source of heat. So let's say an external source of heat gain or loss, for example, depending on whether that's positive or negative. So in addition to the equation that gives you the movement of the heat flow across the bar from left to right, just because of the conduction of the heat in the bar, you may have some device along the object, because it depends on both x and t, that at certain time t and at certain location adds or removes heat at that point in the object. So that appears as a non-homogeneous term. And even though your boundary conditions, let's say, might be still homogeneous, let's say you keep the endpoints of the bar at temperature 0, as a problem, this is obviously not homogeneous. Right? So both the equation and the boundary conditions should be homogeneous. By the way, speaking about the boundary conditions, there is also a classification that I want to mention here, because I'm going to use these terms more often from now on. There are essentially two main types of boundary conditions. So, types of boundary conditions. We have the conditions Dirichlet type, for example. In which you have basically prescribed values of u at the boundary. So that's basically in the heat equation when you have prescribed temperature. For example, u of 0t equals 1, u of 10t equals, let's say, 5. Right? So when you have prescribed values of the dependent variable at the boundary points, that basically makes it a Dirichlet problem or Dirichlet conditions. Then we have the Newman conditions. These are the two major ones we're going to talk about because they lead to those series, familiar Fourier series that we talked about already. These are prescribed values of ux, of the partial of the temperature gradient in the case of heat equation, so of u partial x at the boundary points. Like for example, let's say you have u partial x at 0t equals 0, u partial x at 10t equals 0. This will be, for example, the condition we impose for insulated endpoints. So when the condition states that at a certain endpoint there is insulation, there is no heat flow across that point, that automatically leads to a Newman type condition, right? Because remember, u partial x in the heat equation case is related to the flux. So remember, the flux at the point xt is some constant times the temperature gradient, u partial x of xt. And for now, there is a more detailed classification like Robin conditions or many other conditions. But for now, all others, we're going to call them mixed conditions. And you saw already an example in the context of the Newton law of cooling. Go back to the lecture on that to remember how that works, when you have essentially a mixture of these type of conditions. But in the beginning, when we learn finally the method of solutions, the method of separation of variables, we will deal first with Dirichlet and Newman conditions. All right, so with this preliminary out of the way, let's finally talk about what we call a linear operator and the superposition principle. So stay tuned for the next page. All right, so let's take a look at a homogeneous linear Pde in the form we used in this lesson. So with 0 on the right-hand side. Just like in the ordinary differential equation case, this left-hand side is called the linear operator, and it can be denoted in a shortcut by L of u. So basically the entire Pde can be read as some linear operator equal to 0. So the superposition principle is essentially identical to the one we used in ordinary differential equation. So let's state it here. So it simply states that if u1 and u2 are two solutions of this equation of L of u equals 0, then any linear combination a1 times u1 plus a2 times u2 is also a solution where a1, a2 are constant. And this is easy to verify. We're going to go over one quick example to illustrate. It's just the fact that it's because the derivative, in this case the partial derivative, can be distributed across a summation, and you can pull up the constant out of the differentiation. Nothing more special than that, right? So as an example, let's say we have the equation uxx plus 3uyy equals 0. You know, an example of a homogeneous PDE in x and y. So in this case, u stands for u of xy. And let's imagine that we obtained two solutions. Call it u1 and u2. So this is the linear operator, and because I say that u1 and u2 are solutions, that means L of u1 equals 0, which is to say u1 partial derivative twice plus 3 u1 partial derivative with respect to y twice equal to 0, and we also know that L of u2 equals 0, so that means we know the same about u2. Right, it solves the same PDE. It's not overly difficult to realize what happens if you plug in some linear combination into the equation. So basically, you're gonna plug in a1 u1 plus a2 u2 and then differentiate it twice with respect to x, and then the same thing for the second component, right? Partial y twice. Partial derivative, like any derivative, can be distributed over a summation, and one can pull the constant out. So this will be a1 u1 partial x twice plus a2 u2 partial x twice, 3a1 u1 partial y, 3a2 u2 partial y. And then that allows us also to regroup the terms with respect to u1 or u2. And we get that a1 is multiplied by u1 partial x twice plus 3 u1 partial y plus a2, same thing for u2. Because u1 is the solution of the same PDE, this boils down to a1 times 0 plus a2 times 0 equals 0, which is correct. So I hope you remember also from the theory of ordinary differential equations that if the problem is not homogeneous, this is not satisfied anymore. And it's also important to realize that boundary conditions matter when it comes to superposition principle. So superposition principle works only if the entire problem is homogeneous, not just the PDE. Because, for example, imagine that this equation is combined, let's say, with some boundary conditions. So suppose that in addition to the equation itself, suppose I have a boundary conditions which is not homogeneous. So let's say one is which is homogeneous. Suppose you have I don't know, let's say u of 0 y equals let's say 0, and then u of some other point in the domain, let's say u of 5 y equals 2. If both solutions satisfy this boundary condition, let's say satisfy the boundary condition. So let's say, for example, that you have you're checking to see whether the linear combination also satisfies this, right? So if u1 of 0y equals 0, then u2 of 0y equals 0, then yes, for the homogeneous boundary condition, the linear combination also satisfies the same condition, because it's just a1 times 0 plus a2 times 0, which is equal to 0. On the other hand, if I look at the non-homogeneous condition, so let's say that u1 of 5y is equal to 2, u2 of 5y equals to 2. If I look at the linear combination now, a1 u1 of 5y plus a2 of u2 at 5y, then that's going to be a1 times 2 plus a2 times 2. So of course that may not be equal to 2, right? This may not be satisfied if it's not 0. So that's why this superposition principle that states if I have two solutions, this is also a solution, again refers to homogeneous problem including boundary conditions. We won't need to make this demonstration from now on. Just remember to recognize when it's homogeneous and when it's not, and to look at both the boundary conditions and the equation itself. So we're going to have another page, the last page in this, just to give you another quick example and some other another observation which is important actually for later when we talk about superposition principle. So stay tuned for the last page. All right, so the superposition principle, in the manner we're going to use it actually, it's an extension of what I just mentioned in the previous page. Because think about this, if you have a linear combination of two solutions that is also a solution, the same concept can be extended to 3, 4, 5 solutions, up to infinitely many solutions, provided that the series which ends up being formed using that infinite sum is convergent, which you will see that's going to be the case in our situation. But the idea is that if I plug in a combination of 2, then you can plug in a combination of any number of solutions. So to summarize, and that's really the crux of the matter here, the whole point that it will be our building block for the method of solution, is that if we have infinitely many solutions, so if u1, u2, un, and so on are solutions of a homogeneous linear boundary value problem, then a linear combination of these, which essentially becomes a series if you have infinitely many of them, is also a solution. Under the right assumptions, right? That, you know, under which this series converges and all those good things. This will be the essential result we're going to end up with, because you will see, and I'm going to show you with an example to give you a preview of coming attractions. By imposing those boundary conditions, we end up essentially with infinitely many solutions, none of them by itself being sufficient to satisfy all other remaining conditions. But because we have infinitely many of them, that gives us an opportunity to build a solution in the form of a series, which then we have hope to match with the remaining conditions. In a nutshell, that's the plan of attack, but we should be patient because we'll get to that in due course. For now, I want to give you a little bit of preview, like I said, of coming attractions by an example of two different solutions of the heat equation. So at this point, don't worry too much where they come from. This is the heat equation, and I'm going to choose the interval 0 pi, which is kind of an unusual length for a horizontal bar, but it'll simplify a little bit the format of the solution because of that interval. So check with me that the following two functions are solutions of the PDE. So u1 is minus 2 over pi e to the minus t sine of x. And then u2, another one, is 1 over pi e to the minus 4t sine of 2x. Again, don't worry where they come from. For now, let's just basically, differentiate and see if they do satisfy the heat equation that I provided here. So obviously we need to do some derivatives here. So for the left side, partial t is going to be minus 2 over pi sine of x. That's a constant. We do partial t. And then e to the minus t, and because of the chain rule, that's times minus 1. So u1 partial t is going to be 2 over pi, because minus cancels, e to the minus t sine of x. And let's see if this matches the right-hand side. u1 partial x, now t is a constant, sine prime is cosine of x. u1 partial x twice, again pull up the constant, differentiates cosine, and that gives you minus sine of x. We cancel the minus, and notice that they are equal. So u1 is the solution of the boundary of the of the PDE. I didn't mention any boundary value problem, so that's a solution. Let's do u2. So if I do partial t first, that's 1 over pi sine of 2x e to the minus 4t, and then times minus 4 by the chain rule. Let's combine it with 1 over pi, so that's minus 4 over pi e to the minus 4t sine of 2x. And now we have to do partial x twice, cosine of 2x times 2 by the chain rule. That makes it 2 over pi e to the minus 4t cosine of 2x. And then again with respect to x, now it's minus sine of 2x times another 2 from the chain rule. And now minus 2 times 2 is minus 4 over pi e to the minus 4t sine of 2x. Equal. right? So they are indeed solutions of the of this PDE. So that means because of the superposition principle, we know at this point that some constant times the first function, minus 2 over pi e to the minus t sine of x, plus some other constant times the second solution, 1 over pi e to the minus 4t sine of 2x, is also a solution of the same problem. And like I said, I want this to be previews of coming attractions. You might basically take a hint that it looks like the beginning of a Fourier series. Granted that with coefficients that they don't look like constants, but you'll see where the other coefficients come from. But I hope you'll have some intuition at this point that there are plenty other solutions than just these two. Maybe another solution that involves sine of 3x, maybe another one that involves sine of 4x, and so on and so forth. Maybe you could try maybe to find one just by manipulating these coefficients and see if you can find a third one. At this point, our next topic will be finally the solving, so the introduction of the separation of variable method. And I like to teach that. We're going to stay a couple of lectures on this. And I like to start that section by simply by solving from top to finish an example before we describe the method in a more general fashion. That's another lesson in which you have to go really slow, you know, until you observe every single step. There is, it's very important not to rush anything, to make it easier as we move along. So that's it for today.